Hello, everybody, and welcome to another wonderful day of chemistry. So, today we're going to be starting our conversation about atomic theory. So, what are atoms? What do they do? How can we qualify them? So, I want to actually start by kind of overviewing chapter two. So, it is worth noting that a lot of the material we're talking about was big discoveries at the time, but so much of it has managed to work its way into the cultural identity that a lot of this won't be quite as surprising now as it was once upon a time. So we're going to start with the whole idea of the discovery of atoms and kind of how we built up the definition of what they are. Then we're going to move on next time to talking about atomic structure, and this is going to lead into how we define and distinguish in between different chemical elements, which are eventually built into the very famous chemical phenomena of the periodic table, and how even atomic elements can differ based on their masses, yielding atomic isotopes, and how sometimes things can get a little charged as we can produce ionic species, so same atoms but can have different charges. And then we need to go from this microscopic scale of atoms to kind of a molecular scale. And since atoms are really small, we need a really big unit of conversion, the mole. And then we'll finish off the chapter by talking about how we originally looked at molecular species, which was essentially looking at elemental compositions, which really helped us develop a definition of how molecules constituted. So we're going to go ahead and start today with the basic idea of atomic theory. So to get to the roots of atomic theory, as so much in Western science, we have to go back to the Greeks. So they looked around the world and tried to figure out what were the various elements of nature. So most of you know the theory that won out, which is the four elements of nature, being wind, water, fire, earth. Several other definitions included other elements. However, the one who the Greeks should have listened to would have been Democritus. So he proposed that all matter could be cut down and divided until we reached an indivisible particle, so a particle that couldn't be cut, which in Greek actually literally reads as atomos, something that can't be cut. So, a good way to think about how Democritus saw the atom was as a grain of sand. You go out in the desert, you can keep subdividing the desert until you get to a tiny particle that couldn't be cut anymore, the individual grain of sand. However, he turned out to aggravate most of the other Greek philosophers who didn't believe there could be a vacuum or a space in between these particles. Turns out Democritus was right, Aristotle was a little wrong. And this is a good building block that really wasn't taken up until we got to the 17th century and Robert Boyle came into place. And he started defining these concepts of elements, compounds, and mixtures that we defined last chapter. And this was a really big turning point in chemistry. However, it is worth noting that while Robert Boyle is often referred to as the father of chemistry, he himself was not a chemist, as he still believed in alchemy and kept trying to turn lead into gold. You can't win them all. However, this atomic theory and concepts really ended up taking off in the next generation, where we had Joseph Black, Joseph Priestley, Carl Scheele, and Henry Cavendish, who were able to use this idea of a mixture and take something as simple as air and try and figure out the composition of compounds and elements that were present in air. However, their definitions involve things called phlogiston and dephlogisticated air. They were very cumbersome, and we didn't actually have the idea of things like oxygen or water until we got to one of my personal favorite scientists, Antoine Lavoisier, who, in addition to his other work, was the person who originally coined the term oxygen. So we can thank him for the definition of oxygen. And he really helped move chemistry beyond its alchemist roots. And one of the important things that he brought in was this idea of conservation of mass. So he would weigh reactions before and after reactions and find out that mass in was always the same as mass out. So one of his most famous experiments is he took a red calcimercury. We modernly know this as mercuric oxide. It's a mixture of mercury and oxygen. When you heat it, it decomposes into liquid mercury and oxygen. However, before him, everyone was just paying attention to the solids. He noted that that extra mass had to go somewhere, and it was released as gas. And he did so with quite complex apparatus. However, it is worth noting his original inspiration for trying to figure out this conservation of mass, and that was because he was the tax collector of Paris. And he could never quite figure out why there was always more food coming in to Paris than there was waste products going out. And he figured that there had to be some sort of missing component. And so, in addition to coming up with things like mercuric oxide, he was the first person to realize that we breathed out CO2. That carbon we eat in food doesn't just leave as poop and pee, it also leaves as breath. So, if you want to know where the roots of modern chemistry come from, to a certain extent, it was poop. However, unfortunately, his scientific discoveries were cut short in 1794 because it doesn't matter how much of a philanthropist you are, if you're the tax collector of Paris, the French Revolution will cut off your head. So almost all of his scientific findings were recorded for posterity and published in books by his wife, who managed to survive him. And it was her writings which popularized the idea of the conservation of mass. So it's always important to note the important work of these silent women in science that really helped push it forward. And Lavoisier really is the father of modern chemistry, but the person who actually made sure it didn't die stillborn on the guillotine was Marie Lavoisier. However, the real formulation of chemistry is often contributed to John Dalton, who took up Lavoisier's mantle. And one of his first contributions was called the Law of Definite Proportions. So this essentially stipulates that a given compound is always made of the same elements in the same ratios. So these species were often referred to as saying having the same percent composition, which means that if I have, say, carbon dioxide, it doesn't matter the mass of the sample of carbon dioxide, the mass ratio of oxygen to carbon is always the same. However, one of the things that you should note, and we'll deal with this later, is that when we're working with mass ratios, it's often a little bit awkward because we don't usually end up with whole numbers. So one of the things we'll have to deal with later is turning mass ratios into atomic ratios, which currently we know exist as a 2-to-1 ratio of oxygen to carbon. But we'll pick up this idea later. One of the other important things that Dalton proposed was also called the law of multiple proportions. So if I've got two different molecules made up of the same elements, it should contain a different ratio of those elements. So let's take a look at carbon monoxide. So carbon monoxide is composed of one atom of carbon, one atom of oxygen. It's colorless, odorless. However, under exposure to oxygen, it burns with a blue flame. And it's one of the things it's famous for is that it binds to the hemoglobin in your body. And this is what produces carbon monoxide poisoning, as it displaces all oxygen, not allowing you to breathe. Now we can compare this to carbon dioxide. So this is composed of one atom of carbon to two atoms of oxygen. So it has a different mass proportion, still colorless and odorless, but now it's incombustible. I expose it to oxygen and it won't burn. Not to mention, it doesn't cause poisoning as it won't bind to your hemoglobin. So we have a different ratio, different reactivities. However, it is worth noting, as science progressed, we did find that there could be multiple compounds with the same ratio of elements that come together in a different fashion. So Dalton went ahead and he took all of the previous work of Boyle and Lavoisier, along with his law of multiple proportions, and was able to construct a general atomic theory, which still holds fairly well today. First, he went back to Boyle and Democritus, and he said that all matter is made up of tiny atoms, made up of atoms or tiny indivisible particles. And atoms of the same element are all alike. So if I have all atoms that are all carbon atoms are going to behave exactly alike, but all carbon atoms are going to differ from other elements. So all carbon atoms and oxygen atoms will have different properties. And that we can make compounds when we combine these certain elements in certain whole number ratios. And then finally, this idea of reactivity that we'll address more next chapter is that during chemical reactions, atoms are rearranged, but no atoms are not changed. So carbon atom will stay a carbon atom, and they are not destroyed or created. So if you know how many atoms of carbon are coming in, you should know how many atoms of carbon are coming out. And it is worth noting that most of these rules have held up to the test of time, with some slight deviations. We now know that atoms can be subdivided into certain subatomic particles that we'll talk about more next time. We're also going to, we also found that there may be multiple compounds that can be formed by the same whole number ratios. And finally, under the discovery of atomic physics, it turns out you put enough energy into the system and you can actually change the identity of different atoms. However, turning uranium into plutonium, that's something we're going to have to wait until next semester, as this gets into the complicated ideas of nuclear physics. So this gives us a good starting point to talk about chemistry. So next time, we're going to dive into this first point. We're going to look at the actual atomic structure and what goes in to making an atom. Until then, take care.